I want to go over a couple of questions that we have used so far. Okay, we have about, I want to say about 5 or 6 questions that we have gone over so far, and I want to make sure that every single one of you understands it. Okay, so the first one being density. Okay, and density is just going to be the mass over the volume. Okay, again, where this is the mass and this here is the volume. We also gotta remember that the units for this will be kilograms over meters cubed. Okay, when in doubt, go back and check your units as you're working on your problem. Make sure that everything is canceling out. Okay. Now, we also had other equations for the energy transfer. Okay. The very first one being Q equal the mass times the specific heat capacity, which we use C for it, and delta T. Capital T, I should point out, in which this case, this is the difference in temperature. Okay. Again, Q is just the energy transfer. M, just like density, it's still the mass. Lowercase c is the specific heat capacity. And I'm gonna say that is for the material, okay? The specific heat capacity of the material. Okay, and like I said, delta T is just the difference in temperature, okay? Units for this energy transfer is going to be joules, okay? I do want to point out that delta T in this case is going to be final temperature minus the initial temperature, okay? Next up, we have Q dot, which in this case, we are introducing the unit time, okay? So to represent that, we use Q dot is equal to the energy being transferred over a certain amount of time. So I'm just gonna put it as delta T, okay? Where again, this is just the energy transfer. And lowercase t. Okay, I need all of you to notice in this case that the lowercase t is just going to be the change in time. Okay? It's not the same thing as this over here. There are different t's. This capital delta T refers to change in temperature, okay, different temperature. This lowercase t is the change in time. Now, after we've done all of that, we can move on to, oh, before I forget, units for this will be watts, or we can also use joules per second, where the change in time is measured in seconds. Okay. Now we can have heat flux. Okay. So lowercase q dot, we'll leave it at that, it will be equal to q dot over a. Okay, where this is just the area, and this is just the q dot comes from over here. Okay. And obviously units for this will be watts over meter square. Okay. Now, one of the last equations that we introduced, and this is for radiation, was the following. So we have Q equals to emissivity and Stefan's constant times the area times delta T, which in this case we have the final temperature raised to the fourth minus initial temperature raised to the fourth. Okay. Again, this is just going to be a value that is going to be either given or you have to look for it. But this is emissivity. Constant. Okay. And this is Stefan's constant as well. Now, I do want to point out that this is going to be equal to 5.6696 times 10 to the negative 8. Okay. Cannot forget our units. Never ever forget your units. It's going to be watts over meter square kelvins raised to the fourth. Okay. Let me just fix this right here. I don't want any mistakes about it. And this is raised to the negative 8. Okay. And just like we say, A is the area. And this delta T is just difference in temperature. Okay, so I'm just gonna put it as difference in temperature. And that's essentially it. I can't think of anything else at the moment, but essentially these are all the questions that we have used. And it just depends how we use them, whether we have to find the actual energy transfer or the mass or the difference in temperature or the volume. It doesn't matter how we go about it. These are essentially all the equations that we've used before.